Hello everyone. In this video I am going to explain the assembly level program for addition in 8085 microprocessor. Okay, let's start. So we'll see the different program for addition, assembly level program for addition. So let's start with the assembly level program for any 8-bit, a fixed 8-bit number. So here I am taking one example, say addition of 15 hex and 17 hex. So these two are my fixed data. So let's start with that. Okay, how will you write for any two fixed data? Suppose my program is only for the addition of 15 and 17 hex. How will you write in that case? Okay. As you know, for programming, whatever be the programming, it is assembly language or high level language. For programming we always start with drawing the flow chart. Okay, then probably from the flow chart we used to write the pseudocode or algorithmic steps. Then we write the actual code with the proper syntax. Here, first of all, this is an assembly language program, and in assembly language program, it's a hardware dependent. Okay, it's a hardware dependent. So that is why particularly we will write the program for 8085 microprocessor only. Then these are simple programs, so I hope we need not to go through proper processing. Proper step by following proper steps like the flow chart, then algorithmic step, then the code, or otherwise without doing also we can write directly. So you need to understand the steps. So after understanding the steps, since we are going to write the assembly language program which is the hardware dependent, so accordingly we will write the instruction as per the options or facilities available in 8085 microprocessor. That means this edition of this program particularly for 8085 microprocessor only, not for the others, other microprocessor, because assembly language is platform dependent, hardware dependent. Okay. Now to start with this program, addition of say fixed data 15 and 17. So these are my two datas. So in general what will happen, say y is my output, where y is equal to x plus so z is my output, your z is equal to x plus y. So it is given that x is equal to your 15 hex and your y is equal to say 17 hex. Okay, this suppose for example this 15 and 17 is fixed data. That means this program is to write for adding 15 and 17 only. So first of all you need to understand while writing the program in microprocessor, particularly in 8085, thing is the number one, where will you write the programs? You will write the programs in the RAM, and as we know in 8085 microprocessor the total memory space provided is 64 kilobyte maximum memory space. So the address for which will be in hex is 000, that is the memory space, total memory space for 8085 microprocessor is in hex, it is 0000 to FFFF hex. So this is the total memory space. Okay, total memory space provided for 8085 microprocessor. Now within this space there are some memories for the ROM, and ROM is the essential part of any microcomputing or any computing systems, because in ROM there are some monitor programs are stored. As you know that the ROM is for read only, that is you cannot write into the ROM, but there are few programs stored which are required to operate the system. Okay, so like some monitor programs which we used to call as the monitor programs. Okay. So now you are going to write your program into the memory within the space provided this. So before writing, you should understand, you should know the space, because this space 000 hex to FFFF hex, this space is combining both ROM and ROM. This is the total memory space, maximum memory space. So you should know how from which address to what address is for ROM and which address to which address is for RAM. So you need to find out the memory space for the RAM, and within that RAM you can write the programs, and of course you have to write the programs in a consequence, in a sequential manner, because microprocessor always executes in sequence. Okay, so you are going to write your programs in your memory RAM. Okay, so you need to identify the RAM slots where you are going to write the programs, number one. Then number two, as we know, in case of addition or any arithmetic or logical operation in 8085 microprocessor, you know that it operates always with the data stored into the accumulator. That means before going to operate, say for example in this case the operation is addition, arithmetic addition. So in this case there are two datas, x and y. So any one of the data must be there into the accumulator before the executions. Okay, the result should be there into the accumulator. Sorry, the one of the operand, the data either x or y, must be there into the accumulator, and the other one, suppose x is there in the accumulator and the other one y, can be anywhere in the register like B or C or D or E or H or L, or can be into the memory somewhere whose address, the memory location whose address is in HL register pair, or it can be immediate after the instruction. Okay, there are three options. So therefore, what should be the first step? The first step is to load the data, any one of the data in either x or y into the accumulator. Okay. Second, the data can be immediate with the instruction, immediate after the instruction, second data, or can be in the memory or into anywhere into the register. Okay. Then so the second step, you need to load it into the anywhere in the register, or you can put it into the immediate after the instruction, addition instruction. Okay, or it can be anywhere into the memory, the second data, but the address of that memory location must be there into the HL register pair. Okay, and then third step, you need to execute the operation, that is the addition instruction or addition operation. And after that, as you know, before the execution, any one of the operand is in the accumulator, and after the execution, the result is stored into the accumulator, always for any instruction of addition. Okay, so you may you may keep your results within the accumulator itself, or for further verification or anything, you can take it out from the accumulator, or means copy and paste into somewhere into the memory location. Okay. So let's start to write the programs. So number one, since it is fixed, okay, since it is fixed data, I mean in this case the data is fixed. So my first job is, the first step is to load any one, either 15 or 17 hex into the accumulator. So since it is fixed data, so how will you write the program instruction? What instruction? There are different instructions to load the data into the accumulator, but since the data is already given fixed data, so therefore I can write, say, MVI a comma data. Okay, a comma, that is the normal syntax, but instead of data, what I'll write, say let it be 15. So MVI a comma 15 hex. So that means this 15 hex, the meaning of this is A is you are loaded with the 15 hex data. Okay, So the accumulator is now loaded with 15 hex. This is the meaning. Okay. This is your meaning. Sorry, let it be. Okay. Then after that, once one of the data is loaded into the accumulator, so then the second data can be anywhere in the register or in the memory or immediate after the your instruction of addition. So let me put it in the register B MVI. So B comma another data. So 17. So sorry. 17. So the meaning of this is here B is loaded with 17 hex. Okay. B is loaded with 17 hex. Then after that, so my first data is in accumulator, second data is in B. So now my data is ready inside the processor. Now I can put the instruction for addition. So there are different instructions for addition. Since it is the first data is in accumulator anyway, any one of the data should be there in the accumulator. So my first data is in accumulator, second data is in B. So therefore I can use the instruction add R, ADDR. So where R is this specific B. So add B. So what is the meaning of the add B? Add B means the content of the specified register B are added with the content of accumulator, and the result is stored into the accumulator. Okay. So what does it mean? It means accumulator is loaded with what is there in the accumulator? Accumulator is 15 plus what is there in the B? B is in 17. So it is equal to 2C hex. So this 2C hex is now there in your in your accumulator. Okay. Now you can store that result somewhere. So the result is now in your accumulator. You may keep it as it is in the accumulator, or you may store it somewhere. Suppose store the result in say some memory location. So for storing the content of the accumulator directly into the memory location, the instruction is STS, store accumulator. So store accumulator, you have to provide the address. Okay. Address 16-bit memory address. So let it be say addition of 15 addition and store the result in say 2050. Suppose this is a RAM location 2050 hex memory address, memory location. Okay. So in this 2050 it needs to store. So instead of this address you will write 2050 here, and once stored, so it's finished. So to stop the program execution, the instruction is halt. So that's all, this finished. Okay. Now you see MVI A, 15, it's a 2-byte instruction. Machine cycle 4 T state, machine cycle 2 T state 7. MVI B is also 2 byte, so 2 to 4 byte. This is 1 byte, 5 byte. This is 3 byte, 8 byte. Halt is 1 byte. Okay, let us not consider this because it is to stop. So total of 8 byte. Okay. So while writing a programs, whether it is assembly or high level whatever, while writing the programs, along with the the code should be correct logically as well as syntax should also be correct. But at the same time, it is equally important that you write an efficient program. And efficiency mostly in any programming, efficiency mostly lies on the number of memory location used, I mean the total memory requirement of the program, because memory is directly related to the cost. Okay, and then the computational complexity involved, and computational complexity directly relates with the cost, and cost okay in the directly related to the memory, but the time of execution, which we generally used to call as time complexity, the efficiencies mostly rely on the time complexity. Okay, so time of execution is important, how much time it takes to execute. So as you know, this is a 2 byte, 2 byte, 4 byte, then 5, then 3, 8 byte, total of 8 byte. That means in memory, while you write this program anywhere within this space, of course it should be RAM, so there it will take 8 different locations, that means 8 byte is the size of the, along with the hold it is 9 byte. So total it will require 9 byte or 9 memory locations in your memory. So total your size of the program will be 9 byte. Now time here it is a 70 state, it is also 70 state, it is your 40 state, 7 7 8 8 4 12, and this is also your 70 state, 15 state. Okay, let me say whether STA is your for STA T state is 13 because machine cycle is 4. Machine cycle is 40, state is 13. So here it is 7, T state 7, here also it is T state 7, here it is T state 4, here it is T state 13. Okay. Let me see whether it be the T state is correct or not. Okay, for 8B T state is 7, I think. Sorry, T state 4, yes, correct, T state 4. So therefore total 14, 18, your 31, no? 18, 31, total of 31 T state requires. So total time will be 30 without considering the hold. So 31 into if the processor is of 3 megahertz, so then it is 0.33 microsecond. So that many time is required, 31 into 0.33 microsecond is required to execute these programs. Now let us see whether we can reduce the number of byte as well as the state for this or not. Okay. So since it is the data is fixed in this case 15 and 17, so any number 1 it is fixed, data is fixed. Number 2, as we know, any one of the data must be there in the accumulator, so anyway we must have this instruction, but we may omit this instruction because there are instructions by which you can directly add the data, because the data is already fixed. So therefore I can write this, instead of ADD I can write ADI, add immediately. Okay, ADI the data, so data is your 17. So then what will happen? This is something like the byte, this is a 2 byte instruction, so byte 2 of the instruction, which is the data, is added with the accumulator. So here instead of B, then it will be directly 17. So result is again in the accumulator. Okay, result is in the accumulator. So then you can store the result in that particular location. So in that case, ADI, your the instruction ADI is of 70 states. Now see, this way also it serves the purpose. Now you see the number of the state get reduced. It was 4 number of the state get reduced. So it is 27 now. Okay, earlier it was 31, now it is 27. So of course the total time get reduced. Okay, total time get reduced. Okay, or also the total byte, this is 2 byte, this is also 2 byte and 3 byte, so 4, then this is 7 byte, earlier it was 8 byte, so at least 1 byte get reduced. So therefore this is the perfect program, efficient one for this particular case. So your program should be as per the problem. So problem given here is this, because the data is fixed, that is why I have written it like that. Okay, so this is your fixed. So let me remove this. So this program is done. Okay, so this is your program for addition of 15 and 17 and store the hex and store the result into the memory location 2050 hex. Okay, this is the program. Now the same, this is say fixed program. Fixed program means you are writing the data inside the program itself, which is actually not a good practice. But in this particular case, as I mentioned, the problem itself is to add the 15 and 17. So data is fixed. So thing is that if you would like to, because this same program can be for another two data, say 27, 39 for example, then if you would like to change these two data, say 27 and 39, what you have to do? You have to go and edit the program. Okay, so that is not a good practice. Okay, that is not a good practice. Okay, so therefore now next I will show you another case where addition of any to 8-bit number. Okay, addition of any to 8-bit number. Say the first number, say my first number, the first number, so my first number is stored in the memory location say 2050. That means I am going to store in the memory which is a RAM location say 2050, and the second is in 2051, and say the result is to be stored in 2052. Okay, so how will you write the program? So this is now I am going to write the modular program. So modular program means data will not be there inside the code along with the code, but data will be there in user accessible memory. Suppose memory means user will access the memory, user will not going to edit the programs, because here if user wants to change the numbers data, user needs to edit the program. So I am not allowing the user to edit the programs. So therefore I am suppose fixed some locations for the data. So 2050 for the first data x, say 2051 say y, and the result z will be stored in say 2052, which all are suppose my RAM location. So how will you write? As we know, the first step, the first any one of the data, either from the 2050 or from 2051, either of the data should be placed into the accumulator. Okay, then the second data can be anywhere in the memory, but of course it is already there in 2050, but then this 2051 say should be into the HL register pair, then only it can be added directly. Actually it is indirectly, register indirectly. Then it can be into along with the instruction, but as like this, but here I am not going to use this because I am not going to write the modular program. So this is a fixed one. So therefore the options are my data, second data y can be into the memory, but memory address would be in the HL register pair, or I can put it in anywhere in the register. I can copy it to anywhere in the register like B or C or D or E or H or L. So let us see that. Now first data, where it is, the first data is now in here. Suppose your memory location 2050 is currently holding your first data X. Now I am going to copy it to the accumulator. That is the first step. So how will you do that? So there is a direct instruction direct addressing mode instruction in a data transfer group, which is LDA. Okay, so what is LDA? LDA is your the instruction meaning of the LDA is your load accumulator directly from the memory location. Okay, load accumulator directly from the memory location provided. So what is the memory location? Say 2050. So LDA 2050. That means accumulator will be loaded. Accumulator will be loaded. So accumulator will be loaded with the data stored in 2050 hex. Okay, accumulator will be loaded with the data stored in 2050 hex. Okay, so that data is there in there. Now accumulator is having the first data X. Now second data can be there in the memory, but that say my second memory is 2051, but then this the address of the second data, that is 2051, must be placed in the accumulator, for which what you need to do, you need to store this into HL register. How will you do that? LXIH. Okay, LXIH 2050, because they are in the 2050, you have the second data. Or what I can do is, if I would like to use the same instruction again, that also possible. You see, what we can do is, I can move the content of this accumulator to register say B, or anywhere in the B or C or D or E or H or L. So let it be B. So B comma A. So if I do it, move B comma A, what will happen? Whatever be the data that was there in your A will now copy to B. It will copy the content of accumulator to register P. Okay. So in 2050, whatever be the data it was there, it was now into the accumulator at this step, but that same data is now copied to the B. Now I can use accumulator again. So then what I can use? LDA now 2051. Okay, LDA 2051. So now accumulator will be now loaded with second data. Where is the second data? Second data is in your 2051. So as per requirement, it is any one of the data must be there in the accumulator. At the beginning, I copied the first data which is there in the 2050 to the accumulator. Then in the second step, I copied the same data to B, making A free. Then I copy the data from 2051, that loaded the data from 2051 to accumulator. Okay. So now my first data is in B, that means whatever be the data in 2050, that is in B now, and whatever be the data there is in 2051 is now in A accumulator. So then I can use this 8B. Okay, 8B. So this meaning of the 8B, it is add the content of the accumulator, specified register B along with the content of the accumulator, and result is stored into the accumulator. So this means whatever be the data in 2051 that is there in the accumulator, and whatever be the data in 2050 which is there in the B are get added, and result is in the accumulator. So next last step, you need to store the result STA, store the content of the accumulator into say 2052. So you need to store 20 in 2052 and at last the halt to stop. Okay. Now see, instead of using these two instruction, what I can use, here you see LDA is your 3 byte instruction, this is 1 byte, that is 3 and 4 byte, again 3 byte, that is 7 byte, 8 byte, and here 3 byte, 11 byte. Now it requires 11 byte, and accordingly this is 70 state, 40 state, 70 state, 40 state, 13th state. So accordingly you can add it up for the total time of execution. But instead of this, what I can do is I can use, instead of this, I can use here LXI H comma 2051. So LXI H 2051 means it will this 20 it will load HL register pair with the data, that means the memory address 2051. That means 51 will go to your L, H means HL actually, to 51 will go to L lower byte, and 20, that is higher byte, will go to higher byte register H. Okay. So then this is not required, then this is not required, this particular instruction is not required. Then you can do it, instead of 8B you can put it as 8M. Okay. Now let us see how many byte required. So it is now 3 byte, this is also 3 byte, okay, 6 byte, then this is your 1 byte, because it is LDA, data is copying to the accumulator, and this HL register pair is holding this 2051. So then we can consider this 2051 memory location as the register M. So directly I can use 8M without using this. Okay. Now see how many byte it requires. This is 3 byte. This is your 3 byte, 6 byte, 7 byte, 10 byte, 3 byte. This is also 3 bytes, so total 10 bytes. Earlier it was 11 byte. Okay, with this 11 byte. Now T states, you see earlier it has the 7, 4, 7, and instead of 8B it was, earlier it was 8B, now it is 8M. So this was 7, 4, 11, then 7, 11 and 7, that is 18, and 4, that is 22, and plus 13, forget it because it is anyway required. So 22, up till this is 22. Now how many? 7, this is also 7, 14, but this 8M is also 7, so 21, but earlier it was 18. So you see, time and money, you need to take the decision. Okay, time and money. Earlier the time of execution is reduced little, but number of byte gets 1 more than right now. But now number of byte get reduced by 1, but time of execution will increase, that is it becomes slower. Okay. So it's up to you, you can have this choice. Okay. But according to me, since it is, there is a difference of 1 byte only, but better we think of the time. So let me put it as, say, like this, so that I can minimize the time. Okay. So this is the program for this finally. Okay. But now I can further reduce the time as well as memory size of this program also further also. Let's see how. Instead of doing this, if I am writing like this, or so here anyway any one of the data should be there in the accumulator, and now one thing is considered here is that the memory location of the data, first data, second data, for third data, I mean for the result. So it is consecutive memory location, say 2050, then 2051, then 2052. Okay. So since it is consecutive memory, so better we can write it like at the beginning. If I write say LXI H, LXI means load immediately with the HL in the HL register pair, say LXI H address. So what address I will put? Say 2050. Okay, 2050. That means the 2050 address is loaded into the HL register pair. Okay, H and L will be loaded with 2050 directly. That means this 2050 will go to L and 20 will go to H. Then what I will do is, in my 2050, my first data is there. Okay, my first data, where is my first data? First data is in 2050. So I can use move now 2050 is in HL register, means that 2050 memory location can be considered as the virtual register M. So I can write move A comma M. So what it is? Move A comma M. What is the meaning of this? It will copy the content of the memory location whose address is in HL register pair to the accumulator. So what it will come? Accumulator will be loaded with the data in M. What is M? M is the memory location whose address is in HL register pair. What is there in the HL register pair right now? 2050. So from 2050 the data will come to the accumulator. Okay. So my first data is now loaded in the accumulator, the first job done. Then simply second data, where is my second data? Second data is 2051, just one more than 2050. So I can use INXH. INXH. So what it will be? INXH means it will increment the content of HL register pair by 1. So what is HL register pair? HL register pair was having 2050, now it is incremented by 1. So incremented by 1 means HL register pair will be 2051. So now no longer this 2050 is your M, now 2051 is your M. Okay. So your second data is in M now. M means 2051. So simply use the ADEM. Okay. So ADEM will do the addition of the content of A along with the content of the memory location whose address is in HL register pair. So what is there in the HL register pair? 2050. So whatever be the data there in the 2051, that data, that is my second data, is added with the content of A. Where is my the A is my A is having my first data, now 2051 is having my second data, so it will add up and result is stored into the accumulator. Then store it STA or 2052, or instead of doing this, because it is a 3-byte instruction, instead of doing this, what I can do is INXH, then followed by move M comma A. So you see, instead of doing STR 2052, which is a 3-byte instruction, I can use INXH move M comma A. But in case of move M comma A, because INXH will increment the HL register pair by 1, which becomes 2052. So M means the memory location whose address is in HL register pair. So HL register pair is having 2052. and it will copy the content of accumulator to that memory location. Okay. So, it becomes 1 byte 1 byte 2 byte instead of 3 byte, and it is your 13th state, but here it is your 4th states and it is 7, so 11th state. So, better to use this. Okay. So, this step means for this it becomes 2052, and move a comma m means m will be loaded with the content of accumulator. So, what is m? M is the memory memory location whose address is in HL register pair. What is the in the HL register pair? 2052. So, 2052 will be loaded with the content of A. What is the in the A? A is having the result after this instruction. Now, compare these two programs. So, this is out of the previous one I have already compared. So, this is the best comparing the previous two. Now, along with this is 3 byte, 1 byte 4 byte, then 3 byte 7, then 8, then 3 11. Here 3, 4, 5, 6, 7, 8. So, total of 8 byte instruction. Also, time of execution also here less, because number of this state if you count is less. Of course, there is a halt at the end. A halt is anywhere to stop. Okay. So, according to me, this is the final program considering all three programs I have considered. This is one. In between I have edited one more here, then finalize among that two. This was I finalized, then this is another one for the same purpose, comparing this and these programs. According to me, this is your final program, I mean efficient one. Both will give you the correct results, but this is efficient one. Okay. Hope you understood. Now, we will continue with this addition programs. So, now I will show you the another one, that addition of any 2 8-bit number with carry adjustment. Okay. So, the same program only. So, thing is that in this previous program that I have written, in this case, in this program, as you can see, there is no provision for the carry. If so, here actually the program is for addition of data that is stored in 2050 and 2051, the datas. Now, thing is that once you add these two numbers stored in 2050 and 2051, if there is a end around carry generated, although the two datas are of 8-bit, but there can be a chance of generating an end around carry, that is the 9th bit after the addition. But in this particular program, there is no provision for looking after that carry. Okay. So, that I will do it here. Okay. Addition of any 2 8-bit number with carry adjustment. Okay. So, the program will be the same only, this program only. Only thing is that we need to have a provision for the carry. We need to have the provision for the carry. Okay. Now, in this particular program, there is no provision for the carry. Okay, if there is a carry generated after the addition. Now, as you know, in this addition of 8-bit number, if there is a carry generated, that is obviously 1. If there is a carry, that is a 9-bit generated, which is 1. If there is no carry, means 0. Okay. So, how after this addition, how will we come to know whether there is a carry generated or not? Okay. How will we come to know whether there is a carry generated or not? So, obviously, after this addition, as you know, that this addition or any arithmetic instruction, once you execute any arithmetic instruction, the flags get affected, because in 8085 microprocessor anything or any condition on the result is being given by the flag register only. There is no other provision. Anything, any decision or any conditions that are set or resets after any arithmetic or logical operation is the flag only, the conditional flags only. Okay, different conditional flags only. So after the addition, if there is a carry generated, that means carry generated means 1, that if there is a carry generated, obviously carry flag will set to 1. Now point is that how will we look after, or how will we check whether there is a carry generated or not? So obviously there are two as during my last video where I explained the branching instructions, there, as I mentioned, there are only 8 different conditional branching instructions, okay, for jumping within the same program, by which we can check if or not, if a particular flag is set or reset. Okay, so there are 5 flags. Out of that 5 flags, as I mentioned earlier, that the auxiliary carry flag cannot be used for any conditional, or that means for if or else conditional statements, because auxiliary carry flag is middle carry. So here we are looking into the end around carry, that is carry flag. Okay, so I can use just immediate after the addition, because once at this point addition is done, the result is at the accumulator, and accordingly the different flags are set or reset depending on the result. So here I can check whether the carry is generated or not by the instruction jump on no carry or jump on carry. Obviously that should be conditional, not simply jump. So there are two instructions for checking the carry flag: jump on no carry or jump on carry. So where to jump? Okay, so you can use either of these, jump on no carry or jump on carry. So let us use this jump on no carry. That means if there is no carry, then it will jump. If there is a carry, then no, not jump, right? So where to jump? So for the time being, as I mentioned in the branching instruction, it alters the normal sequence. That means normally what will happen, after this instruction this will execute, after that this, then this, then this, then this, like that, one after another it will execute. But if there is a jumping instruction, it will alter, or which is a branching instruction, it will alter the normal flow. Now since it is a conditional jumping instruction, it will alter the normal flow only when the given condition is true. Now what is the given condition? No carry. Okay, no carry. That means if there is no carry, then only it will jump to a particular level. So I am giving it as a level 0. It's a level 1. Okay, level 1. This is just a level. Practically it will be the memory address to which you need to jump. Okay, so if there is no carry, then only jump. If there is carry, it will not jump. Suppose there is a carry. For example, suppose there is a carry. After this addition here, suppose there is a carry generated. Now it will not jump. If it is not jump, as I mentioned, carry is nothing but your 1. If carry is generated, it is nothing but the carry is 1. So if carry, there is nothing else, only carry can be 1. So here what I will do, for the carry, say I am initializing the C register with say 0 0. Okay, MVIC 0 0. That means here the register C will be loaded with 0 0 data. Okay, 0 0 hex. So this 0 0 is now loaded into the C. This is suppose the C flag, C register I am using for the carry. Now if C is now 0 0, after this addition is done. Once the addition is done, then if there is no carry, then it will jump. Suppose there is a carry. If there is a carry is nothing but 1. So what I will do, I will increment INR C, because if C is already 0 0, if there is a carry, it becomes 1. So no need to add it up, simply INR C will make it 1. Okay, if there is a carry. Okay, if there is a carry, then it will increment. Now if there is no carry, that means what? I am using this C register for the carry. So if there is no carry, yes, true, no carry is true, means there is no carry. Therefore C should remain 0 0. That means this instruction should not execute. So therefore it needs to jump. So where to jump? At this level. So this is my level 1. Okay, this is my level 1. Okay, so that means if there is no carry, this particular instruction will not execute. It will directly go, program control directly transferred to this instruction. Actually, practically this L1 is the address of the program address, program memory address of this instruction. Wherever you have written this instruction, the memory address of this means wherever you have written the opcode for this INX is, that memory location, address of that memory location is this L1. Okay. So jump on no carry, that means if there is no carry, then it will jump. That means C remains 0 0 because this instruction is not executed. If carry is generated, so that means this given condition is not fulfilled, it's false. So therefore it will execute this instruction. So that means C becomes 1. So therefore if there is carry, C register becomes 0 1. If there is no carry, C register still becomes 0 0. Okay, so it's done. Now after the result is already there in the accumulator. So move M comma A will store the result of the accumulator to the 2052 as it is in the same program only I have written. Okay, so then to store the carry flag, to store the carry. So what I will do, I will further increase the HL register pair. So at this point HL register pair now, becomes your now become 2053, and then so now your M is the memory location whose address is in HL register pair, that is 2053. So now move M comma C. So the carry is in C register, so it is now coming to M. So that's all. So that means finally you see the C is initialized 0 0 for carry. Then jump on no carry, that means it will jump if there is no carry to the level 1. If there is a carry generated, then it will not jump. So C register will increment it by 1. So that means here, this means C will be your C plus 1. C will be your C plus 1. If there is no carry, if there is a carry generated, and if no carry, then C remains 0, and these things happens as earlier, and finally the carry is stored in 2053. Okay, so the store the result in 2052, and carry is carry in 2053 memory address. Okay, so this is how we do the these things. Next is your BCD addition. Okay, so BCD means binary coded decimal. So suppose my given numbers that is stored in, suppose the same again I am using this. Okay, the same one thing is that this 2050 and 2051 holding the 8-bit number. Now these two 8-bit numbers are my BCD numbers. Suppose already it's a valid BCD number. So this 2050 and 2051 is holding my two 8-bit BCD number, already valid BCD number. So therefore the result should also be valid BCD. The thing is that if two numbers are already BCD, but then also results may be may not be a valid BCD, it may be an invalid BCD. So to after the addition we have to check whether it is valid or invalid. If it is invalid, what to do? How to check the valid? So that 8-bit result has to be checked 4-bit differently. Lower 4-bit, whether the lower 4-bit is sum is greater than 9 or not, or also the auxiliary flag is set or reset. If either of these or both are true, then it is invalid. Then 6 is added to the lower 4-bit. If not, remain as it is. Then go to the second 4-bit, higher 4-bit. In the higher 4-bit, again it is needed to say whether the higher 4-bit sum is greater than 9 or carry flag is set to 1. If yes, then higher 4-bit is invalid BCD and you need to add 6 with the higher 4-bit. If not, remain as it is. So therefore the same program again. The same thing again. But after this addition, what you need to do? You need to say whether the result is a valid BCD or not. Okay. So how to check that? There is an instruction, already I explained in my previous videos, that there is an instruction called the DAA. So it will, and the meaning of this instruction is decimal adjust accumulator. So it will check whether the content of the accumulator is a valid BCD or not. If it is invalid, it will make it valid. How it does? Already I explained that it will divide the accumulator content in lower 4-bit and the higher 4-bit. First it will check whether the lower 4-bit is a valid BCD by checking the 4-bit sum is greater than 9 or auxiliary carry flag is set to 1 or not. If yes, then it will add 6 with the lower 4-bit, and if not, remain as it is. Then go to the higher 4-bit and again check the same thing along with the carry flag. Okay. So that means this DA will make the your result valid BCD. So rest things are same only thing is you need to add one extra instruction which is DA. So that is your BCD addition. Okay. Next is your n numbers of 8-bit numbers. Okay. So in this also, okay, suppose addition of n numbers of 8-bit, addition of n numbers of 8-bit numbers. The n is your total number of 8-bit datas to be added. That n is suppose stored in 2050, and consecutively from 2051 onwards the datas are stored. That means, say for example, this n is equal to 5. That means 5 numbers of data you are going to add. So in 2050, 5 will be stored. Then 2051 first data 1, 2052 second data, 2053 third data, 2054 fourth data, 2055 fifth data. Then the result is in say 2051 plus n. So that is 2051 plus 5. So that means 2056. The result will be stored and carry will be in 2051 plus n plus 1, that is 2057 continuously. So I am using consecutive memory locations. Okay. So here this n is the is an integer. Now remember, while in writing this program, this n is also in hex. Suppose I ask you to add 10 numbers of data, then you cannot put simply n is equal to 1010. You have to put it as a, because 10 in decimal is equivalent to a in hex, like that. If I ask you to add 15 numbers of data, so then you have to put n is equal to f, not just 1, 5, 15. Okay. Because remember one thing, any numbers in microprocessor based programming is in hex. Okay. So this only will use, the same program only will use. Here actually the DA is not required, okay, because here it is not the, okay. So the same program again here, the same program. Now first of all, in 2050 we will store the n. Okay, so for that what I am doing is what I am using the register is say B. Okay, register B. So the first is your LXI is 2050. So 2050 will now holding my capital N. So that M I am now copying to your say register B comma N. So what is M? M is the memory location whose address is in 2050, whose address is in HL register pair. What is there in the HL? 2050. So it will copy the content of 2050 to B. So 2050 is holding N, and that N is now copied to B. So B will be holding the content of 2050, that is N. So this thing again. Now thing is that here we have how actually a series of data is being added. Suppose data 1, data 2, 5 data, suppose data 1, data 2, data 3, data 4, data 5. Now how it is added? Always you have to, as we know, the accumulator, one of the data should be accumulator, and microprocessor is always adding only 2 data at a time. It is not like together data 1 plus data 2 plus data 3 plus data 4 plus data 5. It is always accumulator, suppose holding data 1, then data 2 is somewhere, suppose in M I am using, M means the memory location whose address in HL register. So in M data 2, so data 1 plus data 2, the result is in accumulator, then that result is added with the data 3, again result is in accumulator, that result is again added with data 4, result is in again accumulator, that result is added with data 5, like that. Okay, it is sort of accumulation. Okay, so therefore I have to initialize the accumulator 0, and I need to run a loop, for loop, n times, capital N times. Okay, so for that before these things, your first is your counter, I mean 2050 is loaded in HL register pair, then your counter that M goes to B, so that B is now holding N, and N behaves as a counter, capital N behaves as a counter. Then now see, in 8085 there is no provision to say whether the count goes from 1 to that particular, say for example capital N is equal to 5, but there is no instruction in 8085 to say whether it reaches 5 or not, but there is instructions to say whether a counter say decrementing and decremented till 0 or not. So it is always maximum to 0 in case of 8085 while running a loop. Okay, like in a higher language, high level language, what we do, we initialize with 1 and go up to the maximum count, but here we'll start with the maximum count, say 5, for example 5, then 5 4 3 2 1 0, like that. So for that counter will be used as a B, register B, because B is now holding my capital N. Okay, therefore then since it is accumulation is done, this addition is through accumulation, so therefore I have to initialize the accumulator. So for initialize with 0, so how will you initialize the accumulator with 0? I can use MVI comma 0 0, or I can embed the content of accumulator 0 0. There are different instructions. So but out of that, if I use XOR A, because XOR A means A is XORed with A. Okay, it is A is XORed with A. So when anything is XORed with A, same data is suppose 0 XOR 0 is 0, 1 XOR 1 is 0. So therefore A is XORed with A is 0. So that means at this point accumulator becomes 0 0. Okay, accumulator becomes 0 0, and this is for the carry. Okay, now this is not required, this is not required. Okay, this is not required. Then INXH, so 2050 was holding N, then accumulator get cleared, C is 0 0, here you cannot use XRA C, right, because there is only A with A, there is not C with C directly, there is XORing instruction to make it. Here also we are making C00. Likewise, I can use MVI A comma 00 also, but to minimize the number of byte, because XOR A is 1 byte, MVI A comma 00 is 2 byte. So I can use here MVI A comma 00 also. Then also accumulator is 0. But to reduce the number of byte, I am using XOR A. So it is the best practice. Always try to reduce the number of byte, and also t-state, number of t-states. Okay. So then this MVI C for the carry, it is 00. Then 9x is, so HL becomes 2051. So therefore directly I can add because accumulator is now 00. 2051 is holding my first data. So first data is added with 00. Result is in 00. Result is in accumulator. Then this here is not required because we are not going to say go for the BCD. Then jump on no carry. Okay. If there is no carry, if there is suppose carry, then carry will be incremented by 1 as it is previously is done. If carry is there, it will be incremented by 1. If there is no carry, then what is to be done is need to decrement the counter. As I mentioned here, we are not going to increment the counter, we will decrement because there is no provision to check the maximum number, but there is a provision to check the 0. Okay. So the counter is in B, right, capital N is in B. So what I will do, one count gone because here the first number get added, so one number gone. So therefore I will put it DCRB. So B is decremented by 1. Suppose B N was 5, now it becomes 4 now at this stage. At this stage it becomes 4 now. Okay, it becomes 4 now. Okay, it becomes 4 now. So after this DCRB, that loop will be this part, this part will be repeating. This part will be repeating. Okay, how many times? 5 times if n is equal to 5. So how will we looping it? Okay, by checking whether the counter is 0 or not. How to check the counter is 0 or not? Because if the counter B goes to 0, I mean decrement and decrement and decrement till once it is 0, so then that flag will set to 1. Okay, so what I can do is here I can use jump on no 0, say level 2. Okay, level 2. So if B is 0, then it will not jump because it is no 0. Okay, if B is 0, it will not jump, but if it is non-zero, then it will jump. Jump on no 0. The given condition is no 0. Suppose yes, no 0. Suppose B was 5. Now at this stage, first stage it is 4. So yes, it is no 0. So where should it go to get the second number? So it is goes to this level. Okay, it goes to this level. So B becomes 4 here, suppose. So no 0, it goes to this. Again it goes to increment 2052, then M becomes 2052, it add M, so data 3 will be added. Result is accumulator. Carry, if carry it is happening, if no carry directly decrement, now it becomes 3. Again no 0, it goes to here. So data 3, data 4, data 5. Once the data 5 goes, if B is 5, then it becomes 0. So once it is 0, then it will no longer jump. So if it is not jump, it will then increment, further increment it. So it will not be 2052 then, it will be 2051 plus n. Okay, it will 2051 plus n. Okay, and this will every time changing. This is also not always 2051. It will be changing every time. Okay, it will every time changing. So to what we can say here is, okay, it will be changing every time. First it is 2051, then 2052, then 2053, then 2054, then 2055, like that it will go on as many as B. Okay, and after that finally once it is 0, it will not jump. It will then finally again increment that many. Okay, and then finally the result is need to store. So for storing the result again, that the last will be stored here. If suppose you would like to store the result somewhere in a different location, then you can use STA directly. Okay, or you can use again LXI with that memory location, the given memory location. Suppose instead of this, if I am giving some extra memory location, say for example 3050, so then what you can do here, instead of this you can write LXI H, 3050, then move M, A, then INX H again and move M, C. So this is actually here 20, now it is 20 and last one. Okay, so that's all for the 8-bit addition. So this program becomes the addition of array of an 8-bit number. Now finally for the 16-bit numbers. Now as you know, there is a direct instruction for 16-bit addition which is called DAD. Okay, so now for the 16-bit addition, as I mentioned, there is a direct instruction DAD. Okay, so here also again I am using this for initialization of the carry. Now since it is 16-bit number, one memory location cannot hold 16-bit, so therefore you need to have two consecutive memory location. Number one, to store first 16-bit number, and second, similarly another two consecutive memory location for storing second 16-bit number. Okay, then after the addition also result will be at least 16-bit and there may be a carry. So for the result again two consecutive memory location is required. Okay, now since the DAD instruction, as we know that the direct 16-bit addition instruction works always with the HL register pair, as like in normal addition is always added with the content of the accumulator. So here instead of accumulator, the addition is done with the content of the HL and result is stored into the HL register pair. So therefore any one of the data, that is 16-bit data, should be there in the HL register pair. So to load the data directly into the HL register pair, there is an instruction LHLD. So what is LHLD? LHLD means load HL register pair directly from this memory location. Now HL register pair, but here it is only one memory location is given. Suppose my first data, the lower byte is stored in 2050 and higher byte is stored in 2051 for the first 16-bit data. Lower 8-bit is stored in 2050 and higher 8-bit is stored in 2051. So therefore LHLD means load HL directly from this memory location. So what happens? Already I explained in the instructions, while explaining the instructions said in my previous video, that from the first memory location, that memory location is given along with the instruction, that is for the lower byte, that is 2050. From this 2050 data will loaded into the L. Then from 2051 data will be loaded in H. Okay, so therefore this instruction is loading my first data into HL register pair, first 16-bit data into the HL register pair. Now since there is only this instruction for loading HL directly, there is no such instruction for loading DE or BC. So therefore we need to execute this instruction again for the second 16-bit number. But before that we need to make a copy of this data which is now there in HL register pair to some another pair. So there are three pairs only, HL, DE and BC. So there is an instruction XCHG, that is exchange the content of DE with HL. No other pair, only DC, DE and HL. So once you execute this XCHG, so the content of DE get exchanged with HL. So what is there in HL? HL is holding my first 16-bit number to be added. Now it goes to the DE, and whatever be the data there was in DE, DE that goes to HL, that is not our concern. But DE now is holding with my first cell. So at this point, DE register pair is now holding the first 16-bit number. Then again I am using LHLD 2052. Why 2052? Because 2050 and 2051 goes here. gone already. So therefore LHLD 2052. So 2052 data will goes to L, from 2053 data goes to H. So now HL is holding my second 16-bit data. So my first 16-bit data is in a DE register pair and second 16-bit data is in HL register pair. So DADD, DADD means that is the instruction for the 16-bit addition. That is only one instruction for the addition of 16-bit data directly, which is DADD. D for DE register pair. So it will add DE register pair with HL register pair, and the result is stored into the HL register pair. So result is stored in HL register pair, okay, with after the addition of the content of HL with the content of DE, okay. So result is in HL. Again this procedure is same. If there is a carry, it directly goes, where there is no carry, then it will go to the storing. If there is a carry, the carry I have initialized in C register, so carry becomes 1, and SHLD is directly stored because result is in now HL. So SHLD will directly store the results into 2 consecutive memory locations. From L it will go to the 2054. That means my lower byte of the result is now stored in 2054 memory address, and the result of the higher byte, that is in H, will go to 2055 memory location, okay. And the carry is in C, so I am copying that C to accumulator, and then STSA 205455 goes here, so 2056 I am storing the carry. So 2054 is holding my lower byte of the result, 2055 is holding my higher byte of the result, 2056 is holding my carry. That's it, okay. Hope you understood this program. So this all about these are the different addition programs. Try to understand this, please follow this, okay. If you find any difficulties to understand this or any queries about this program, kindly get back to me, okay. I'll kindly inform me and I'll get back to you. Thank you for the listening.